Hello everybody, my name is Sriram Pillai, and this video is an instructional video about acetals and hemiacetals as part of the Chem 207 curriculum at William & Mary. First, I'll go over what is an acetal and what is a hemiacetal, the mechanism to form one, the function that it has as a protecting group, and why acetals are so important. So first of all, let's go over what is an acetal. So acetals typically take the form of having an RO group bounded to a carbon with another OR group, and then either an alkyl chain or an H, forming the remaining two bonds. If it's an H, it would be called an acetal because it's from an aldehyde. If it has another alkyl chain, it would be called a ketal, but still both the acetal and ketal fall under the umbrella of acetal. So now let's try to go over the general mechanism on how to form an acetal. Let's use this molecule as an example. This can be either an aldehyde or a ketone, so the R's here can be either an H or anything else. So the first step here is to react with an H+, and I'll say R2OH. R2OH here is an alcohol. This would form an alcohol bonded to that initial carbonyl C, an OR2 bond to that initial carbonyl C, and then the original two R groups. This is called the hemiacetal, meaning halfway to the acetal. If you repeat with H+ and R2OH, you obtain the same molecule, but the OH has been replaced with another equivalent of OR2. And this is the acetal. So now let's dive into the mechanism of forming an acetal. Let's start off with this molecule. Now, if you remember naming for ketones and aldehydes, this molecule is called 2-propanone, or commonly it is known as acetone. In the real world, we use this molecule as a nail polish remover, or in organic chemistry lab, we use it as a rinse to remove organic residues. So here the R groups are just CH3. So let's start the mechanism. The first step is to protonate the carbonyl. The first step is to protonate the carbonyl O, not just the carbonyl. So that that lone pair will attack the H, and then we'll be left with an O, double bonded to the carbonyl C, but this time it would just be bonded to an H. That's 3 bonds and 1 lone pair. So the O will have a positive charge. The point of that first protonation was to make this carbonyl C available for the second step, which is the nucleophilic attack. So here I'll just use MEOH as my alcohol. So this lone pair will come and attack right here. This bond will flip up. We would be left with an O that is completely neutral, single bonded to the C. And here we have an O bound to an H and an Me with 1 lone pair, hence a positive charge. The next step is to deprotonate the alcohol that just attacked. This can be accomplished by several different molecules. Here it can be accomplished by H2O or MEOH, or even the conjugate base of the acidic environment that we're using. So if we're using sulfuric acid, we can use HSO4 minus. So here I'll just use H2O. We'll just grab that H, and it would the bond will move to the O, or the electrons would move to the O to neutralize the oxygen. And then we'd be left with the alcohol up top. And now we have an OMe that's completely neutral. Now the fourth step is to protonate the original carbonyl oxygen. This is in preparation to get it to leave as a leaving group, as water. So since we're in an acidic environment, this is quite simple. Just like the very first step, the lone pair just attacks the H, and we would be left with the oxygen bond to two hydrogens with one lone pair bonded to the C, and then we have OMe. And then the water would just leave as a leaving group. And this would leave, so this would net us H2O, but then we would also have a carbocation. This is where, in the sixth step, an alcohol would attack again. So since we used MEOH, the second equivalent of MEOH would attack this carbocation, and then we would be left with, again, a carbon with 4 bonds, 2 of them remaining being the original 2 like alkyl groups, and we have OMe here, and then we have this O bond to an H, bond to an Me with a lone pair. And this oxygen has a positive charge. The seventh and final step is to deprotonate this alcohol. This can again be accomplished by several things. Here I'll use MEOH. Those electrons will move back to the O, neutralizing the molecule, and we'll be left with the acetal. It's important to note that each and every step is completely reversible, and that for the formation of a hemiacetal, you don't necessarily need to have the reaction occurring in an acidic environment. You can have it occurring in a basic environment as well, only that that reaction would not proceed to the acetal. Additionally, you don't have to really use 2 equivalents of alcohols, such as like MEOH, 2 equivalents of that. You can use a vicinal diol. So this molecule has 2 alcohols attached to it, 1 carbon away, and this, if we were to use this molecule instead, in an acidic environment with our 2-propanone, we would get, first we would get this molecule with an OH, which is as expected. But then, rather than another molecule coming in, we would just have that alcohol on the vicinal diol come and replace that alcohol. So we would be left with something like this. A cyclic acetal. And this leads right into our next discussion on the use of acetals as a protecting group. So let's consider this molecule. If we were to react this molecule with LAH, which is a strong reducing agent, in H plus and H2O, if you haven't learned yet, when LAH is reacted with a ketone, you're left with an alcohol, as the ketone is reduced to an alcohol. The same thing happens with esters. But if you were first to form an acetal, an H plus with a vicinal diol, you would form this molecule. And then if you were to react with LAH and H plus H2O, you would find that only the ester actually gets reduced, while the acetal is not even perturbed. Since we know that acetal formation is reversible, we could just use H plus and H2O to bring back the ketone that was in our initial molecule. And we would also get back our vicinal diol. So we can see that here we've achieved a sort of regioselectivity because we use acetal formation as a protecting group for a ketone. The LAH only reacted with one functional group in our molecule. Now let's move on to something a bit more interesting, the importance of acetals in the real world. So I first want to talk about a molecule called polyoxymethylene. This is what it looks like. It's called polyoxymethylene. It's also called an acetal. It's also called a polyacetal and a polyformaldehyde. Now, it being called an acetal is a bit confusing, but that just happens to be a common name for this polymer. But yes, it is a polymer, and that's what the N and the brackets indicate, that multiple subunits of this subunit are connected in a chain to form polyoxymethylene. This molecule was discovered by Erman Staudinger, if I'm pronouncing that correctly, definitely not. And this net him the 1953 Nobel Prize in Chemistry. But the issue was that this molecule was not commercializable. There was really no way to produce this molecule en masse. So that's where DuPont comes in and discovers this synthesis. So they started with aqueous formaldehyde. Both our groups are hydrogens here, and it's aqueous. And they reacted it with H plus H2, they reacted with H plus and ROH, which, as we know, is just simply one of the two steps of acetal formation. So we form a hemiacetal here. Do know that since the formaldehyde was aqueous, there's still some H2O here. So now the next step is an extraction. We want to dehydrate this solution so that we're only left with the hemiacetal and no H2O. So this is anhydrous hemiacetal. It's also called hemiformal because it was derived from formaldehyde, but again, just like a ketal, it still falls under the umbrella of a hemiacetal. Now we heat this up, and that brings us back to the formaldehyde, but this time no longer aqueous. Now there's this process called anionic catalysis. The mechanism is quite complex and it's not in the scope of this class, but the idea is that this formaldehyde, looks like I forgot to draw the H's, is now sort of converted into this subunit. And then also is able to polymerize along with similar subunits, so you achieve this sort of molecule and so on. And this is what POM is. So why is POM important? It's used in everything. Characteristically, it has a very, very low coefficient of friction, making it very slippery. It's used on a lot of metal on plastic bearings and gears. So pretty much anything you can think of that uses either of those things, bearings or gears, with metal or plastic, use POM. And interestingly, it's also used in biomedical contexts, inside diabetes monitors, inside pen injectors, inhaler, syringe components. It's particularly useful in biomedical contexts because the low coefficient of friction makes it easy to slide and slip, like in things like syringes. It also makes it easy to sterilize surfaces that are POM because bacteria and things like that could not really hang on to the surface. Now I want to talk about one more application. I want to talk about cancer. With cancer, the basic idea is that there are cells that are uncontrollably growing and proliferating. And this leads to tumors, and depending on where the tumor is and the severity of the rate of growth and proliferation, you get death. But it's pretty much obvious that for this to happen, there needs to be a lot of ATP. ATP is adenosine triphosphate, the energy molecule, and when broken down into adenosine diphosphate and an inorganic phosphate, you get energy. So, but one thing to notice is that, first let's go over the metabolic cycle. First there's glycolysis, which would net you 2 ATP. Then there is some prep step, and then there is the Krebs cycle, which nets you 2 ATP. And then there is the electron transport chain, which nets you around 30 to 34 ATP. So you can sort of see here the majority of ATP is generated in this last step. And so you'd assume that cancer cells utilize the electron transport chain to get as much ATP as possible and then grow uncontrollably and proliferate as much as possible. But this is actually not the case. This paradox is called the Warburg effect or paradox. And it is that cancer cells prefer anaerobic glycolysis over anything else. And this is even in aerobic conditions. So this means they're really only netting 2 ATP per molecule of glucose. The key here is that in anaerobic glycolysis, there is lactic acid formation. And this would mean that in cancer cells, there is high H+ and therefore a high pH. So there's a lot of research ongoing on using this feature to identify cancer cells, but what I want to talk about is this paper right here, which utilizes drugs that have acetals in them to activate and inactivate the drug as you approach the cancer cell. So this diagram right here is just a reverse reaction of acetal formation. Remember, it's reversible. So here they forgot to put in the vicinaldiol. But this would react with the aldehyde in an acidic environment, and eventually hemiacetal, you would get to the acetal. But the drug itself would be in the stable state as an acetal. The idea is that once it enters a cancer cell where H+ is high, it would cause the acetal to degrade into the aldehyde and the vicinaldiol. From what I understand, I don't have access to the full paper. One of these molecules, most likely the aldehyde itself would be the drug molecule, and the vicinaldiol would be just an inert molecule. And so the drug is activated only inside the cancer cells. And this is in comparison to something like chemotherapy, where the treatment occurs throughout the body and causes side effects like hair loss. The drug would only be activated inside the cancer cells because of the higher pH inside the cancer cells. And this would improve anti-cancer activity, but would also make sure that this activity occurs only in the cancer cells. And this is a major sort of obstacle in anti-cancer treatment, because cancer cells are really just cells, they just happen to be more active. Similarly, in bacteria, the inside of a bacterium tend to be a bit more acidic because cytoplasmic proteins evolved to be more sort of comfortable in acidic environments. So I don't believe it's as effective, but you still see some improved antibacterial activity by using an acetal-based drug. So that's pretty much it for the lecture. I hope you learned something, at least that acetals are interesting. Thank you for watching my lecture.